It's time for 2.10 step functions. You already know this unit's all about different types of functions, and step functions are pretty unique. You're going to see them pretty soon. As always, describe the effect a given parameter has on a graph. We know that means the same thing as transformation. Graph a step function given its equation. Of course, graphing is part of it. So, a step function, what is it? Well, we see a little visual over here. It's a type of piecewise function. We see that over here. And it makes sense, right? Because we see different lines that are not connected. There's different pieces, okay? And we can see each piece is a horizontal segment. And we know that anytime a function equals a single number, that gives us a flat horizontal line. So that makes sense why we see 2, 4, 6, and 8. Okay? And this also has a rule, right? Piecewise functions have rules. So take a look. These rules show specifically where all of these line segments are. Okay? X, that shows you where the line is. Well, it's trapped between X values of 0 and 1. We see that over here. 0 and 1. At the flat line of Y value of 4, X value is trapped between 1 and 2. Okay, some key things to point out. Open dot on the left. Let's use a green to show this here. Open dot on the left, that comes from the less than. Okay. Then when we have the solid dot on the right, well, that comes from the less than or equal to, right? And these values affect the height. So 2, 4, 6, and 8, just like we see here. So now we're starting to understand the step functions on a graph, but let's make sure we really understand this. Go ahead and look at the graph. We're looking at a real life situation where we're dealing with a parking lot. Here's the hours parked, and here is the cost in dollars. Have you ever been to a parking lot or a parking lot structure where it says something like the first hour is free, and then it's $3 every hour after that? Well, this is just like that, and you're gonna see why in just a second. How much do you have to pay if you park for exactly 3 hours? Well, let's find 3 hours and go up until we hit a solid line or a solid dot. Boom. We're going to pay $6. Okay. What about 2 hours and 10 minutes? 2 hours, 10 minutes would be just past the two. So if we go up, boom. Again, we are at $6. Interesting. So are we rounding up or down? Well, clearly we're rounding up, which is not so good for the customer, but good for the company, right? Because think about it. If you stay 1 minute past 2 hours, you're going to pay $6. So the person, who do you think was happier here when they got their parking ticket when they left and they had to pay it? Probably this guy, right? He's thinking, man, I just made it by the last minute. If I didn't get out at that last minute to make the 3 hour mark, I would have had to pay $8. And then the person orange line here, parked for 2 hours, 10 minutes, they're thinking, man, if I just left 10 minutes earlier, I would have only had to pay $4. So that's how that works. Now, there are two different types of step functions. They're called least integer and greatest integer. And here are the similarities and the differences. So here are the different categories of step functions. Here's the least and all of that information and the greatest. Okay, on a graph, the least line segments are going to look like this, with the open dot on the left, solid dot on the right. We also call this roof because if you look right here, you see these little inward lines near the top. Now I know that's kind of small, so I'll draw it nice and big. Okay, that is what it looks like on a function in the function, like it says over here. And these line segments are how it looks on a graph. Okay, so let's keep going down the list of least. So least, the first point you graph is always the solid dot at the origin. Boom, right there. Okay, and then we say least left. That's because your line segment is going to go over to the left with your open dot over there. Okay, now that is for least. And a saying I use that might help you is at least I have a roof over my head. That helps you visualize which one of these to use. And then least left is also very useful. And I demonstrated that a moment ago. Okay, and that is just like the example we saw a moment ago where we're rounding up. Now, greatest is similar, but reverse. Solid dot on the left, open dot on the right, meaning we're rounding down. For example, if you were maybe 16 years old and 9 months, and someone asks you how old you are you going to say 17? Are you going to say 16 and 9 months? Probably not. You're probably most likely going to say 16, which means you're rounding down. That's why you see the solid dot at the lower end. Again, similarity, first point you always graph is a solid dot at the origin. And from there, if least is left, then greatest, also known as floor, is right. And you guessed it, it's floor because you see those little inward lines at the floor, at the bottom. This saying, that's the greatest floor I've ever seen. Silly quote, I know, but if it helps you, use it. Okay, and like I said, we are rounding down there. And just to be clear, when I talk about these graphs, when I say the first point you graph is the solid dot at the origin, I'm talking about the parent function, okay? And with this type of function, it is probably a good idea to start by graphing the parent function, just the first line segment, so you can apply those transformations properly. So let's practice graphing right now, okay? So we're going to try to first graph the first step of the parent function, that first line segment. Okay. Solid dot at the origin. Okay. That's easy. Graph the rest of the step. So if we're graphing a least integer function, least left. Boom. That is the first step of the least for the parent function. Okay. If you were graphing greatest, how would you do it? Well, you'd go exactly in the opposite direction. You would start solid dot at the origin. If least is left, then greatest is right. That would be the first step of the greatest integer step function. Again, this is for the parent function. Okay. And then you would apply transformations for A, H, and V. We know these guys, right? Athletic A, dishonest H, elevator V. You know what they do, okay? But let's talk about A for a moment because A is a little bit different, okay? Because we're used to just stretching or compressing vertically with A, right? So here's what I want to say. The first step will not stretch or compress. All other steps will. Okay? So, we're going to start by following these directions. graph the first step of a least integer step function. There it is. Okay, this is least. Okay. And now we're going to look at all of the steps for the least parent function. There it is. Notice they are all 1 unit long and 1 unit tall. Up one, over one, up one, right one, up right, up right, up right. We can keep going forever. Okay? That's how it's spaced out. Again, we just graph the first one because then we can apply transformations from there. Okay? Take a look as well at the least integer step parent function with all possible transformations. Write that down. Okay. So we know athletic A vertically stretches and compresses. Okay. And remember what I said before. For A, the first step, it's highlighted there. Clear to see. The first step doesn't stretch or compress, but all other steps will. So what would change if A was equal to 2? Okay, so let's draw it out. This is the parent function with no transformations happening. But what I'm asking you is, what if we made A 2? So we put a 2 out front like that. Okay, and the graph you see here is this. But what would this one look like? Hmm. Let's see if you got it. Here it is. Okay. You have your parent step function here. Okay. And notice, like I said before, each step is 1 unit long and 1 unit away from each other vertically. So if you're starting with your first step here, you're going down by 1 and up by 1 to find your next steps. But if you have A of 2, well, that means your steps are now getting steeper. You're now moving them up 2 instead of 1. They are 2 units above or below the other. Okay, that's what that athletic A does. Notice the first step is in the same place, but obviously these steps are much steeper, right? And we already talked about what the function looks like. You see it again right there. And we know H and B, that's just going to move things left, right, up, and down. But let's also take a look at the greatest integer step function. Here is the parent for that. The only real difference is you have these lines at the floor. And on the graph, what's the difference? Well, your line, your first step goes off to the right. Okay, after you plot that first point at the origin. This is really the powerhouse, that first step, which is nice, right? One little short line at the origin. So you've learned about some transformations, and you're no stranger to dishonest H and elevator V, so let's see if you can answer a few questions here. It says the graph represents the function over the interval -2, 6. Hmm. So what do you think the gray part of the graph is? Look at the function carefully and look at where those line segments are carefully. Okay, answer to yourself. I'm going to show you the answers in a moment. What about the blue? What do the blue lines represent? Again, look at the function. Look at the blue lines. And finally, what does it mean when it says here, the function is over the interval -2 to 6? They asked us to graph, they told us the graph represents the function over the interval -2 to 6. Where do you see -2 and 6? That's a good place to start. Well, here are the answers. The gray section, that's the parent function. Okay, and this is roof, right? And what type of function goes with the roof? That's least. Okay, least, roof, greatest floor. So, gray lines are the parent function. Blue lines are the transformed function. These purple arrows should have been a bit of a giveaway. We're moving everything down 2, and you should know by now if you're adding or subtracting something at the end of a function, that's elevator V. So everything's moving down 2. That's the only transformation happening here. And when you see the words over the interval with some values, another way to think about that is the graph to graph the function between those x values. So in this case, we want to graph our steps between the x values of -2 and +6, and that's exactly what you see. Now, it just so happens that those are the last values on our graph, but oftentimes you'll see more values going off to the sides. And if you didn't have that interval, what would happen? Well, you'd be graphing a stairway to heaven, and that's not what we're doing. Okay, you've learned about all the transformations. You've had a lot of practice with functions. So see if you can get these 3. And let's check it out. The first thing you always want to do was what? Solid dot at the origin, always, no matter what. Okay? Now, this has feet on the floor. So this is greatest. So greatest right. This has a roof. So it's least. Least left. Okay? And this last one is also greatest. Okay? Did I put another? I did put 2 solid dots there. Let's undo that. One moment. This should be a open dot there. There we go. Now we're in business. We have our first line segment for all 3. We need to know where to move them. Okay, so let's look at this. What's happening? We have +3 inside those symbols with the X. Well, that means that's dishonest H. So we have an H value of -3, which means we move to the left 3 units. So this solid dot will move over 1, 2, 3, putting this line segment right there. Okay, that's the only transformation. And remember, for the parent function, we had line segments 1 long and then up 1. So we should go up 1, right 1, up 1. Oh, let's try that again. Up 1, right 1, up 1, right 1. That's exactly what's happening. So we're graphing the rest of those in place. Okay, obviously those were pre-graphed. But what's interesting here? Well, they wanted this graph over the interval of -2 to +2, but that first line segment we graphed doesn't fit in that interval, does it? So guess what? It goes away. We just needed it to help us graph what we really needed. Same thing with that first segment of the parent function. Okay. What about the next one? This is elevator V, just like before. So we move that line segment up 1. So this moved up to there. Again, that was the only transformation. So over 1, up 1 steps between -2 and +2. So our graph looks like this. And finally, this one is the most challenging because there's 2 transformations. You can do either one you want first, but make sure to graph that parent function segment before anything at the origin. Me personally, I would choose to go with dishonest H first. I think moving left, right, up, down is a bit easier than stretching and compressing. So dishonest H, we see H is looks like -3, so it's actually +3. Sneaky guy. Move into the right 3. So 1, 2, 3, solid dot right there. And the rest of the line segment follows. We see that. Now what happens? Well, we also have an A value of 2. So just like before, that means these steps are getting 2 times as steep. Instead of going up once, we're going up twice. So over once, up twice. And they wanted that between the intervals of 3 and 6, which is exactly what we have. So that interval specifies how much of the step function they want to see. On your quiz, you're not just going to be asked about step functions, which is why we have a little review here of absolute value functions and different piecewise functions. So go ahead right now and practice these. You're graphing for both. And let's see what these look like. There they are. Remember, for an absolute value function, the vertex is at the origin with a slope of 1 on the right, and that's mirrored on the left. Okay. Then we have dishonest H and elevator V. So left 3, I would just focus on the vertex, and then down 1. Boom, vertex moved to right here. And of course, everything else follow. So black line is a parent function, green line, transform function. And the piecewise. We start by graphing -2x. Since there's no designated y-intercept, we know it's at the origin. Slope of -2, which would make this line continue like this, but we were given a rule. If x is less than or equal to -1, which is why we chop off this line anywhere we see a point with an x value that is not -1 or something less, right? X value of 1, or sorry, -1, -2, and so on. And the second part of this piecewise function, f of x equals x. Well, what's that mean? That means we have a slope of 1x, or, well, the slope is just the number, right? So we have a slope of 1, but we know slope is rise over run, so 1 over 1. Again, no specified y-intercept, so it's, again, the origin. And that rule comes into play. Only x values greater than 1. Notice, if it's not or equal to, there is a solid dot. If it is or equal to, sorry, if it is not or equal to, it's a open dot. If it is or equal to, it's a solid dot, meaning that -1 is included. Here, 1 is not included. And with that said, we are done with our step functions.